So today we're going to continue to look at hypothesis testing and looking at these steps and what we do on each step with a hypothesis test. So here are the four steps that we looked at in yesterday's lesson. Create the hypotheses, null and alternative, collect the data, summarize it with a test statistic, determine how unlikely that test statistic would be if the null hypothesis is true, and then finally make a decision from all this information that we're being told. So we're going to start today by looking at the detail of each of these steps a little bit more and then walk through a couple example problems to help clarify what's going on in each of these steps. So when you're making the null and alternative hypotheses, I mentioned in yesterday's lesson that rather than think about the null hypothesis as no relationship and the alternative hypothesis as there is a relationship, we did that interpretation for chi-square. For a z-test, you would rather think of these as equations or inequalities. And the null hypothesis is always going to be some form of equality. That could be an equal sign, that could be greater than or equal to, that could be less than or equal to. Okay? A lot of times we'll just say equal to, but really, I mean, it could be implied that it's greater than or equal to or less than or equal to. This leads to the alternative hypothesis as being whatever other possibilities are remaining. So let's say, for example, the null hypothesis is that P, our population proportion, is equal to 50%, 0.50. So our alternative hypothesis would mean that, well, the population proportion is either bigger or smaller than that 50%. Okay, so to consider both of those, the inequality that we'll have would be P is not equal to 0.50. This is what is called a two-sided alternative hypothesis. Okay, the population proportion of interest is not equal to the null value. We don't know if it's bigger, we don't know if it's smaller. Okay, it's just different. It's not equal to it. Okay, we don't care about the direction. So it's kind of intentionally vague. And this is important for a step later on in the process in helping us determine the magnitude of our conclusions or the strength of our conclusions. The other alternative hypotheses are one-sided. Okay, this not equal to is two-sided. It could be smaller, it could be bigger, and we show both directions with that not equal to sign. For the one-sided hypotheses, this would strictly be greater than or less than for the alternative hypothesis. So let's say we had a null hypothesis that was P is less than or equal to 0.50. Okay? Now again, a lot of times you would just see P is equal to 50%, and our alternative hypothesis would be P is greater than 50%. Okay, you cannot have an equal to in the alternative hypothesis. Okay? But if you look at these together, all three possibilities are counted for. Right? If you have two numbers, let's say two numbers A and B, A can be equal to B, A can be greater than B, or A can be less than B. Those are the only three things that are possible. It's called the law of trichotomy. Officially, all three of those considerations need to be accounted for. Okay? Sometimes informally, though, like if it wouldn't make sense for P to be smaller than 50%, we would just say P equals 50, and for this alternative, P is greater than 50%. Okay? Obviously, in our final option here, we could have a one-sided alternative hypothesis if the p is less than, we're interested in it being less than that null value of 50%. So we could have p less than 0.50. This would technically go with a null hypothesis of p greater than or equal to 50%, so that all three options are accounted for. But again, sometimes you'll just see that as equal to in the null hypothesis. All right. So to wrap up in this first step, a two-sided alternative hypothesis is when it's not equal. Okay? A one-sided is if it's simply greater than or simply less than that null value, that number that's given in the null hypothesis. On to our second step, this is where we're collecting the data, looking at summarizing it with a test statistic. This is called a standardized score. Okay, we're using a z-score for this. It measures how far away the sample proportion is from the null value in units of standard deviation. So this is how it compares to what we did with our z-scores, because remember, our rule from sample proportion says that this will fit onto the normal distribution, with the center of that curve being our expected population value. So our standard deviation is found by using that rule for sample proportions. Okay? We see that down here where we have our null value. Okay? This is our expected or anticipated value, so P is our population's proportion. That is the null value times the complement, so 1 minus P, divided by our sample size, and then take the square root. That is our standard deviation step. And we are finding this test statistic by our sample proportion minus the null value. This is following our z-score equation. So looking at x minus the mean, or in this case the null value. We could use mu, we could use, I guess, p in this case, and then divided by our measure of standard deviation, which is right here. And this equation is given on our equation sheet, our updated equation sheet for this final unit. Our third step, determining how unlikely it would be to get this test statistic if that null hypothesis is true. This is where a p-value comes into play. So we work through and we get a z-score that, going back to what we did in the first semester, we look at the z-score chart, and that decimal that is represented from our z-score chart, we are interested in what is in the tail. Okay, so if it's on the lower end, and we had an alternative hypothesis that was one-sided, then that means that we are interested in this value down here. Okay, that would be the p-value that is given directly from the z-score chart. Okay, again, well, on our next step, we'll talk about the importance of that p-value. We could also have a one-sided alternative hypothesis if we're looking at the population value being greater than this, so we could have it on the upper end. Now, this is where you need to be careful, because if you look up a z-score that's in the, let's say, 97th percentile, and we don't care about the 97% that's down here, we care about the 3% that's up here. Okay? You're interested in what is in the tail. Okay? If you have a two-sided alternative hypothesis, you don't care if it's smaller or bigger. You care about both. So what you have to do is, when you get your z-score and you look it up on the chart, okay, you get the value that's in the tail, you need what's down here and what's up here. So you need to multiply that by 2. Okay, this is unique in this case because you have a symmetric data set. So you know whatever's in the tail on the left side is going to be what's in the tail on the right side. Okay? So again, our alternative hypothesis in this case, if it were a two-sided test, is that p is not equal to whatever value you have. Okay? You get that p-value for the the tail, the amount of data in the tail, and you need to multiply it by 2 to get what the official p-value would be. Okay? We'll see this again in our examples. Our last step here, making a decision. The researcher compares that p-value to a predefined level. We talk about this predefined level as the alpha value. Okay? Typically that is 0.05. So if our p-value is less than 0.05, the alpha value, then we reject the null hypothesis and accept the alternative. Okay? That's what we're talking about down here. The true population proportion is significantly different from that null value, differently according to that alternative direction. Remember that p-value is a probability. What you're saying is that if you have a probability that's less than 5%, so let's say, for example, our p-value is 0.02, you're saying that there's a 2% chance that you could have this, what you expect to have in the null hypothesis, and get a sample where that value is this far away from what was expected in the null hypothesis, just due to chance variation alone, just to it being a fluke. A 2% chance of that happening is pretty rare, because it did happen. It happened in your sample. So, because it's less than 5%, you interpret that as meaning it's not a fluke. It would be unlikely for it to be a fluke, that this is really what's happening in the population, because this is what I got in my sample. Okay? Now, if that p-value is greater than that level of significance, greater than 0.05, let's say for argument's sake it's 0.10, 10%, now you're saying that you expect this in the null hypothesis, you got this value in the alternative, that there's a 10% chance of that happening just due to natural variation. 10%'s not rare enough based off of our definitions here. Anything less than 5% would be rare enough. We got 10%. 1 in 10, that's not rare enough. So in this case, we would fail to reject the null hypothesis. The true population proportion is not significantly different from the null value. We don't have any evidence to reject that null hypothesis and accept the alternative hypothesis. So let's take a look at a couple examples here. Continuing with our quarters or semesters. Our null hypothesis, the proportion of students at the university who oppose switching semesters is 50%, 0.50. Okay? So here we're going to say that p is equal to 0.50. Now this p is population proportion. It is not the p-value that we see. We overuse this p letter. The alternative hypothesis, the proportion of students at the university who oppose switching to semesters, is greater than 50%. Okay? So p is greater than 0.50. This is a one-sided alternative hypothesis because we only care if it's bigger than that. If it were less than that, then we don't have an issue. Okay? There's a minority of students who are against this change, so they're going to make the change. They don't have an issue with that. Okay? They're only considering making this change if a majority of the students are against it. This is what I was talking about, how, well, really officially this null hypothesis would be p is less than or equal to 50%. We need the equality there. We don't really need the less than sign in this case. All right? So we just typically write it as equals. Okay? But it is important that this alternative hypothesis, we have the inequality sign is greater than. So step 2, we collected our data, sample of 400 students, 220 of them, or 55%, were against it. That 55% is our sample proportion, p hat. Okay? So 55% are opposed to it. So their standard deviation calculation from our rule for sample proportions we take our null value, our p-value, and 50% times the complement, also 50%, divided by sample size, 400, take the square root, we get this value. Okay. And that is our standard deviation measurement. So our test statistic from our z-score equation, okay, p hat minus p, divided by our standard deviation, I'll just put a sigma there, we get 2. This is 2 standard deviations above the mean. So, continuing on, if we were to look this up on our z-score chart, which again, maybe you have from the first semester or it's linked at the top of our lesson page today, we are doing a z-score calculation. So our 50% of what we expected is at the center of the curve. We are 2 standard deviations to the right of that to get our 55%. Okay? So that would mean that we have this data in our tail. Okay? And we could find that, again, if you look it up on the chart, you get about 97 point something percent of the data, almost 98% of the data is below. We care about what is above. So you have to do 1 minus that 98%, 97%, and you get this, 0.0228. This is our p-value. Okay? It is less than 0.05. Okay? And this is a one-sided alternative hypothesis. So that is our p-value. If it were two-sided, then we'd have to get this on the other end and multiply it by 2. But it's not. So we have our p-value that is less than 0.05. We reject the null hypothesis, accept the alternative hypothesis. The true population proportion opposing the switch to semesters is significantly greater than 50%. We have evidence of that. Let's look at another example here. There's a government report that says 67% of teens live with both parents, but a survey was done and it said that 84% of teens lived with both parents. Now these are significantly apart from each other. We want to know if that survey population is maybe different than what this government report was saying. So we're going to go with the government report as our null hypothesis, our accepted population value. For the population of teens represented by the survey, the proportion living with both parents is 0.67. Okay, so our null hypothesis, pretend that's an H, our null hypothesis is that P is equal to 0.67. Our alternative hypothesis, we want to know if they are different. Okay, look at the question of what you're interested in. Does the survey population differ? Okay, it'll either say they're different or you're interested in that one is greater than or one is less than. Those words tell you what the alternative hypothesis should be. If we are just interested in if they're different, then that means that this is two-sided. P is not equal to 0.67. So, this is a two-sided alternative hypothesis. That's going to be important for our last step with the p-value. So, moving on, step 2, we collect our data. Survey of almost 2,000 teens, 84% of them were living with both parents is what we got in our survey. So, standard deviation calculation, you see that null value, okay, p, 0.67 times its complement, divided by sample size, square root. This is our standard deviation measure. So we perform our z-test. Our value, p hat, 0.84, minus our null value, 0.67, divided by our standard deviation, we get 16. That is an incredibly large number for this type of problem. Remember, here's our bell curve. Okay, there's our center, 0.67. Standard deviation is like 1%, so 0.68, 0.69, 0.70. We keep going all the way to the right until we get to 84%. That's 16 standard deviations away from that center. This is way off of our z-score chart because that decimal in the tail would be essentially 0. Okay? So the proportion is essentially 0. You're going to get some cases that take you off the chart. Okay? If you're using the chart, then you just say it's the p-value is approximately 0. Okay? Now remember that in this case, this was actually a two-sided alternative hypothesis. So technically, we're multiplying this by 2. Well, 0 times 2 is still 0. Okay? You're still well below that 0.05 level of significance. So p is low. We reject the null hypothesis and accept the alternative hypothesis. We believe that we have evidence that the proportion of teens living with both parents in the population represented by this survey is significantly different from the population of teens living with both parents in the U.S. I meant to take that away. We're not doing that today. All right, so that's all for right now. Tomorrow we're going to talk about if we made a mistake, what that error interpretation looks like, and what are the consequences of that mistake.